little Eppendorf tube, right, with your unknown in there. So this is our experiment. Now in there, let's say that we have our unknown, and also we have an acid and also a base. So they wouldn't be layered like this, they'd be all mixed in, but it looks confusing to just mix them all in. Now we know the acid or base is going to be a polar compound, so a non-polar compound, excuse me, so it's going to be an R, and I'm going to abbreviate this as COOH, or essentially an R NH2. And then let's just abbreviate the unknown here is just being like, how about an R double bond O? So that's fluorinone. Let's just say that I gave you fluorinone, okay? And in this case, R is equal to benzene. All right. So the first thing that we're going to do is we're going to take this and we're going to dissolve in diethyl ether. And we're going to put this thing into a vial. So that vial is going to be like a 4 ml or 5 ml conical vial. So rather than draw out vials over and over again, I'm just going to draw a box here. Base here is RNH2. The acid is RCOOH. And our unknown is RC double bond OR. And right now, this is in ether. So it's all dissolved in ether. Now, what we're going to do is we're going to add to this something that will react with either the acid or the base. Doesn't really matter which one we do. So what I want to do here first is I want to add in sodium hydroxide aqueous. Okay. Now remember, we want to do this twice, so I'm going to write 2 times. Okay. Now, so when we do that, we're going to form 2 layers, and here's how we're going to show the 2 layers in these separation schemes. We're going to come way down here, so, and then come over here. So this is going to be your bottom layer. So when we add an aqueous solution to ether, the bottom layer is your aqueous layer, and the top layer is your organic layer or the ether layer, right? So H2O up here, diethyl ether. So after we do those 2 extractions, we're going to be left with a couple of things. So, well, what does NaOH react with? That's a base, it reacts with an acid. So then down here below, you have RCOO minus. Right? Now, to test whether or not it's present, so you would actually have this in a separate test tube right now. This is where you pipette it out to test whether it's present, because it's dissolved right now. You would add an acid. So you would add HClAQ. And then what you would do is you would look at this thing and you would look to see if you have a PPT. So if there is a PPT present, then you'd say, aha, I must have had an acid impurity there. Right? So you can visually see it inside of your test tube. Okay? How do you know how much acid to add? You use litmus paper. So you just keep throwing in the acid until it's acidic. So that's how we would do this. All right, so in the top layer, this is your ether layer. In the top layer, you're going to have your organic unknown, and you will be left down here with your base. Now, if we want to separate that base out, we need to add something that reacts with that nitrogen. So we're going to add here H3O plus, right? So the way that you would do that, you would go back in the hood and you would grab hydrochloric acid. Now when we add HCl to ether, we form 2 layers. Okay, now the bottom layer is going to be your aqueous layer, and the top layer is your organic layer. So bottom layer, let's talk about what's in that bottom layer. So remember, HCl is going to react with the NH2 part to form NH3. So we get this. And then top layer, you'll have your unknown essentially. Now in the real experiment, you don't know whether or not I gave you an acid and or a base. We don't know that, right? So if you're carrying out this experiment, you couldn't see that anything is in that bottom layer. This is where you pipette things off. You put this bottom layer in a second test tube. So here, where we show that, we're separating our layers, right? Same here. We separate, pipette out the bottom layer and the top layer. Right, so you pull out the bottom layer and put it somewhere else, and you're left with the top layer. To test whether or not that's present in solution, because it's dissolved, we need to add a base. So we add NaOH, AQ, throw it some litmus paper in the mix there. So you put a little bit of that on the litmus paper and test for its presence. That would give you an R NH2. And then this, if it's present, would be a PPT. So you'd literally see like, solid sitting in this thing. Same thing like down below where you have this, you would see solid in there. So you're looking for solid. If you see it, then that would have meant that you had that present as your impurity. Now, we're left with this. So remember that this is your ether. Right, so in here you have your ether. But if you recall, there's a trace amount of water present. Just because the ether and the water, when they touch each other at a surface interface, a little bit of water goes into the ether. So what you would do is you would take this and you dry with sodium sulfate. Now remember, dry just means that doesn't mean that you're sticking a paper towel in it and drying it. That means you're removing water from that layer. Okay, and then we would remove that sodium sulfate. Okay, probably by just decanting or pipetting it into another test tube or something. And then we would evaporate to dryness. Right, so evaporation, hot plate, right, water bath, test tube, hood. Right, so you evaporate. Now, to test what your unknown is, you would then take the melting point. So we know here, I've given it to you as fluorone. But remember in the experiment, it could be 1, 2, 4, 5 tetrachlorobenzene, fluorine, or triphenylmethanol in addition to fluorinone. So everyone, as they go through the separation scheme, would have an isolated unknown right here. It might not be fluorinone. In this case it is because I chose it. But we would determine its identity by taking the melting point. So folks, just a couple other details to wrap up here with extraction. So as far as choosing solvent, it's not something that you typically have to do as a sophomore level organic chemistry student. But we want to pick solvents which readily dissolve the substance to be extracted, right? Shouldn't react with the substance, right? Shouldn't react or be miscible with the aqueous layer. Typically we want to pick something that has a low boiling point. That just makes it easy to evaporate at the end. And densities determine what's on top and what's on bottom. Right? We mentioned diethyl ether has a density of about 0.7. Most organic solvents are below 1, with the exception of methylene chloride, which is 1.33. Now, there's some technical things here involved with our separations too. Is that when you mix these two layers together, so what you would do is you would take your conical vial, right? You have your solutions in there, so you'd have your top layer, your bottom layer. This could be your ether, aqueous layer, And then what we do is we put a cap on that. And then we mix. So we want to shake the layers back and forth because we want these things to come in contact with each other. And we do that by gently shaking it, right? And we're looking for emulsions. So emulsions are where we get this kind of weird middle layer. So if you look in at like the two layers, what you'd have is this weird little kind of layer in the middle that looks like a cloudy little nebula. So if that happens, you just have to let it sit, or you can centrifuge it to try to get those layers to kind of compress into each other and form just a nice interface there. The other thing that happens is that when we shake these solvents together, we build up some vapor pressure up here. So you see a little bit of pressure. And after we shake, we have to unscrew the cap and we have to vent. So what you actually hear is as you open it up, you might hear like a little pff, like a poof sound. So we just do that to avoid caps being popped off, especially if we have glass joints or something like that. So it's really easy to remove the layers. We just have to always remember we remove the lower layer. So here we have dichloromethane. We add water. So in this case, water's the top, DCM's the bottom. Stick your pipette in. You slurp it up carefully. Now, practically speaking, and we'll get a chance to do this at some point in time, sometimes you have to do this in two separate movements because it can be hard to get every last little drop out. But you pull off that bottom layer and you put it over there. So that's if you want the bottom layer. You can pipette it directly out. If you want the top layer, you get it by removing the bottom layer. Again, you're just still removing the bottom layer. Right? So here you have water. Right? You've added ether to this. You pull out the bottom layer, which is water, and you're left with the desired layer there. A couple other little concerns here. You want to make sure that when you're picking solvents, you want the organic solvent to not be miscible with water. Now, some solvents are going to dissolve a little bit in water, and water in that solvent example that we kind of talked about before was diethyl ether. So sometimes we have to dry layers, and that's where we use that sodium sulfate. The other thing that can be used sometimes is magnesium sulfate. They're common drying agents. So the other thing that we have to do sometimes is we have to dry even more. So diethyl ether is an example of a compound that really likes water. So I want to show you guys the last little thing here about what we might do in this type of situation. So let's imagine that we have a centrifuge tube. We'll just make it kind of short here. All right, full of ether. Okay, and in that ether, we've separated everything out. This is the end of our extraction. It's right before we do the drying and all of that stuff. In that ether, we have a little bit of trace water. So this ether has a small trace amount of H2O in it. So sodium sulfate can be used to help that, but depending on how much you have in there, sometimes you have to add too much sodium sulfate. So before we do that, we say that we have to dry. So we must dry the layer, and we do that by adding saturated sodium chloride. So with NaCl saturated. So that's saturated, it's aqueous, by the way. So how does adding water to that help dry the layer more? Well, the sodium chloride has been added to the water to such an extent that it no longer dissolves. So it's very polar. It has a lot of ions in it. So what we're going to get there is we're going to get two layers. So we got a top and a bottom layer. And down here in the bottom layer, we have a lot of sodium chloride. And here again is your water layer. Up here, this is your ether layer. Okay. Now, the water that was in this ether layer has a choice to make. Stay in the ether layer or go and hang out down here where we're very polar and welcome. So those water molecules actually move down and come into the bottom layer. And then we'd remove the water layer. So I'll just kind of do this down below. Right, we stick a pipette in and remove, the lower layer. Right? And what we're left with then is still, it's not perfect, but now we have less water in there. Right? So before, we had 3 molecules of water here. Of course, there's more than that. Let's put 1 more over here, and that way we can kind of show here, here's your ether. We can show that, well, you still have one molecule of water left. It's more than that, but we've decreased the amount by 2/3. So then what we do is now we have a layer of ether with a lot less water in it. So then we dry further with sodium sulfate solid. Right, so you put that stuff in there. So here you have your ether, and then down at the bottom is your solid Na2SO4.10H2O. Right? And then what we would do there is we remove that, and then we would be left with our vial or centrifuge tube here with essentially just ether in it, and then we would evaporate that. So pull this thing over a little bit. So last step, you evaporate. Right, so it's an additional step. I know up above in our previous little discussions we said, well, you just dry with this. That works a lot of the time, but sometimes we need to do a little initial drying with a saturated sodium chloride solution.